Okay, let's do the next problem. Evaluate the inverse Z transform of x of z equal to log 1 by 1 minus a z inverse for mod a less than mod z. Okay, this is a very good problem. You are given x of z equal to logarithm of 1 by x of z equal to logarithm of 1 by 1 minus a z inverse, and essentially it should be a natural logarithm, and given mod a less than mod z. Okay, so now we are in a trap because we are encountering a logarithmic function here. We don't have anything that relates how to evaluate z transform of a log function. So we will think of some tricky properties, because we have to remove logarithm, right? We have to definitely remove logarithm. How will you remove logarithm? There are actually two methods by which you can remove log from a function. The one method is by taking e to the power something, right? E to the power of x of z will eliminate the logarithm and will give you 1 by 1 minus a z inverse. But still we are in a problem because we don't have anything that tells how to find out e to the power x of z. Okay, so we will give up that idea. So what is the second method that removes logarithm from a function? It is nothing but differentiation. Very good, it is differentiation. So if you find out, if I can write x of z equal to log 1 by 1 minus a z inverse, then also I can write x of z is equal to, what is logarithm of 1 by 1 minus a z inverse? It is nothing but minus log 1 minus a z inverse, right? Okay, now if I find out d by dz of x of z, that will give you minus 1 by 1 minus a z inverse. Thankfully this log is gone, but it is not over. We have to find out the derivative of this function 1 minus a z inverse also. So that becomes 0 minus 1 into a into z inverse 2. Okay, and that will end up in minus 1 by 1 minus a z inverse into plus a z inverse 2. Okay, let me there. Now I am, for some specific reasons I am finding out minus z into d by dz of x of z, right? Minus z into d by dz of x of z. D by dz of x of z, we have already a function here, so I'm multiplying minus z to it, and that gives plus, right? Here is a minus and here is a minus, so plus z into a z inverse 2 by 1 minus a z inverse, which will give you a into z inverse by 1 minus a z inverse. Okay, so I will consolidate whatever we have done. We have started with the question x of z equal to log 1 by 1 minus a z inverse, and I have written it using the property of logarithm as minus log 1 minus a z inverse. Then I found out minus z into d by dz of x of z, and I wrote an answer a z inverse by 1 minus a z inverse. Okay, so in frequency domain I have found out some expressions, that is minus z into d by dz of x of z. What would be its time domain equivalent look like? What would be its time domain equivalent look like? We have the property of Z transform, which is called derivation or frequency derivation property, which says the Z transform of n into x of n will be equal to minus z into d by dz of x of z. Okay, so from that property, whatever we have in this Z transform domain, its time domain will look like n into x of n. Okay, so I can boldly write n into x of n will be the inverse Z transform of this term, right? Because we have found out minus ZD by dz of x of z is this thing, so its inverse Z transform should be n into x of n from this property. Okay, so we will try to evaluate some inverse Z transform for this term and arrive at n into x of n. Okay, so okay, fine. Okay, from standard knowledge, what is the inverse Z transform of 1 by 1 minus a z inverse given mod z greater than a, mod z greater than mod a, because it is given in the question, mod z greater than mod a. What will be the inverse transform? It is nothing but a raised to n u of n. Okay, it's a right sided signal exponential, a raised to n u of n, right? Therefore, but what we need is this thing. Okay, so we have a 1 by 1 minus a z inverse whose inverse Z transform is a raised to n u of n. So let me ask you, what is the inverse Z transform of a by 1 minus a z inverse? It should be a into a raised to n u of n, because it follows linearity property, right? So a by 1 minus a z inverse will be having inverse Z transform a into a raised to n u of n. Okay, that is nothing but a raised to n plus 1 u of n. Okay, therefore what we want is this a z inverse by 1 minus a z inverse. So I am multiplying this expression with z inverse. So what is the inverse Z transform of z inverse into a by 1 minus a z inverse? It's very simple. If we are multiplying a transform with z inverse, that means in time domain it is shifted by 1 unit. Okay, it's from time shift unit, time shift property. Okay, so time shift property will give you a raised to n minus 1 plus 1 into u of n minus 1. Okay, that is equal to a raised to n u of n minus 1. Okay, so is the answer over? No, because whatever you have here, its inverse Z transform is found out, and as per the property we know the inverse transform is n into x of n, but we need x of n. Okay, so we can write, therefore n into x of n is obtained as a raised to n into u of n minus 1. Therefore, what is x of n? X of n is equal to a raised to n u of n minus 1 whole divided by n. So this is the final answer. Alright, the next question is, the step response of a discrete time LT system is s of n equal to a to the power u of n, a to the power n u of n for a less than 1. Okay, find the impulse response h of n of the system using Z transform. Okay, so we have to make use of Z transform to find out the impulse response h of n of the system, and you are given the step response. So step response means immediately you can write the input signal x of n equal to unit step signal u of n. Therefore its Z transform is what is the Z transform? It is z by z minus 1. Okay, for mod z greater than 1. Okay, now the step response s of n means it is the output of the system to the input step signal. Okay, so y of n is equal to, it is given as a raised to n u of n, a raised to n u of n. So immediately you can write what is the Z transform of y of n, y of z, which is equal to z by z minus a for mod z greater than a. Okay, and a is a value less than 1. So what is impulse response? You cannot get impulse response directly, but you can have the transfer function directly. Transfer function is Z transform of output divided by Z transform of input for no any initial conditions. You know what is y of z and you know what is x of z. So y of z is z by z minus a divided by x of z is z by z minus 1, which will result in h of z as z minus 1 by z minus a. Okay, but here is a catch. What the catch is, you have to observe the degree of the numerator and degree of the denominator. You can see both turn out to be 1. So the numerator and denominator have the same order, degree. That means this is an improper transfer function. Okay, so whenever you find an improper transfer function, be thorough that its time domain will be having an impulse signal. So its time domain of an improper transfer function always results in a del of n in time domain. Okay, so in frequency domain, if you encounter an improper transfer function, then its time domain will definitely give you an impulse function. Okay, let us see how it comes. For finding the inverse transform, if you find inverse transform only, then you will find h of n. Okay, so to find inverse transform, let me write h of z by z. I'm just dividing h of z by z. That means we have to divide by z in the RHS of this expression also. So it becomes z minus 1 by z into z minus a. Okay, and I am writing it in the form of partial fraction, a by z plus b by z minus a. So a equal to, the shortcut to find out a is the a can be evaluated by multiplying z, the denominator of a, throughout the transfer function, and evaluate this transfer function for z equal to 0. Z equal to 0 turns this into 0, denominator to 0. So a equal to z and z cancels, so minus 1 divided by minus a equal to 1 by small letter a. Okay, so a equal to 1 by small letter a. And what is b? B equal to, similarly you take z minus a and multiply it with the transfer function, so z minus a cancels, and evaluate the rest with z equal to a, because z equal to a turns this denominator into 0. So this b becomes a minus 1 by a. Okay, therefore h of z by z is equal to, instead of a by z, I can write it as 1 by a by z, plus instead of b by z minus a, I can write a minus 1 by a into 1 by z minus a. Okay, now what is h of z? H of z equal to, I can cross multiply this z to both the terms, so 1 by a into z by z cancel out, so a minus 1 by a into z by z minus a. So this is the transfer function h of z, which is in a proper form to evaluate the impulse response. Therefore, taking inverse transform, h of n is equal to, what is the inverse transform of 1 by a? What is the inverse transform of 1? You can always know del of n gives z transform as 1. Okay, so 1 by a into del of n will always give you 1 by a. So inverse transform of 1 by a will give you 1 by a into del of n. Okay, plus a minus 1 by a into, what is the inverse z transform of z by z minus a? It is a raised to n u of n. Okay, now a raised to n is here, a raised to a is here, so we can write as a raised to n minus 1 into a minus 1. Therefore, finally, h of n will be equal to 1 by a times impulse plus a minus 1 into a raised to n minus 1 into u of n. So this is the final answer, and as I have told earlier, we can see an impulse signal in the output response because the transfer function is an improper transfer function. So that concludes the answer. Okay, the next question is, given x of n equal to 1 for mode n less than or equal to n1 and 0 otherwise, find the Fourier transform. So the question is to find out the Fourier transform, discrete time Fourier transform of x of n DTFT. Okay, because this is a discrete time and aperiodic signal. Okay, so okay, for fair answer, we can always try to plot the signal at least roughly. because otherwise you may end up in the wrong answer. So without taking much time, you can plot the signal. Okay, so the signal will come something like this. Okay, so the signal is 1 for mod n less than or equal to n1. That means the samples are all 1 within plus n1 and minus n1, and for all other time instance this will be 0. Okay, so this is x of n. So it has sample 1 from minus n1 to plus n1. Okay, now we have to find the Fourier transform, and as per definition, Fourier transform of the signal x of e raised to j omega is given by sigma over n equal to minus infinity to plus infinity x of n into e raised to minus j omega n. That is equal to, you don't have to summate it from minus infinity to infinity, but only from n equal to minus n1 to plus n1. And in this duration, out of this duration, all samples are 1. So 1 into e raised to minus j omega n. So now let us try to expand the signal. So the leftmost value will be for n equal to minus n1, and that turns out to be e raised to minus j omega into minus n1. Let me write it as e raised to plus j omega n1. I hope you understand it. E raised to plus j omega n1. Okay, plus second sample will be for minus n1 plus 1. Okay, the second sample here will be minus n at minus n1 plus 1. So e raised to minus j omega into minus n1 plus 1, that will turn out to be e raised to plus j omega n1 minus 1. Okay, e raised to plus j omega n1 minus 1. So I can write it as e raised to plus j omega n1 minus 1 plus etc. It goes up to in between at n equal to 0. At n equal to 0, you put n equal to 0, the sample will be 1, purely 1. Plus, what is at n equal to 1? The immediate next sample here, it should be e raised to minus j omega, plus for n equal to 2, it becomes e raised to minus j omega 2, and it goes etc. up to, what is the last value for n equal to capital N1? It becomes e raised to minus j omega capital N1. That's it. No more samples. Okay. Right. So this, as you know, will be a geometric progression with first term e raised to j omega n1 and a common ratio e raised to minus j omega, and the number of terms. What is the number of terms? There will be, you can see there will be 2n1 plus 1 number of terms, right? 2n1 plus 1 number of terms. Because why? Because there are 1 to n1 in the positive direction, so n1 samples. Minus 1 to minus n1, again n1 samples, so 2 n1 samples, and there is a sample at 0, so 2 n1 plus 1 terms are there in this GP. So this is a finite GP, and you know what is the sum of a finite GP, right? What is the sum of a finite GP? It is given by Sn equal to a into 1 minus r to the power n by 1 minus r, where a is the first term, n is the number of terms, and r is the common ratio. And why r is e raised to minus j omega? I've already told you, any term divided by its previous term will give you the common ratio. So instead of taking this term divided by this term, you will always get the right answer, but it will be very quick if you take this term divided by this term. Both the answer will give you the same result, which is the common ratio. So e raised to minus j omega is the common ratio, r. So the sum is, we can express it as, okay, a is e raised to j omega n1 into 1 minus r is, what is r? We have told you it is e raised to minus j omega. So e raised to minus j omega whole raised to, number of terms is 2n1 plus 1 whole divided by 1 minus r. R is e raised to minus j omega. Now it's only a matter of simplifying this. This is equal to e raised to j omega n1 into 1 minus e raised to minus j omega into 2n1 plus 1, because a raised to m whole raised to n becomes a raised to m into n whole divided by 1 minus e raised to minus j omega. Let me take some space here. Okay, that is equal to, now this can be simplified by e raised to j omega n1 as it is. So I can take, so here it is e raised to minus j omega into 2n plus 1. I can take the half of the exponent, right? E raised to minus j omega into 2n plus 1 whole divided by 2 outside of this bracket. That could simplify this further. So e raised to minus j omega into 2n1 plus 1 by 2, half of this outside. Okay, so in order to maintain this factor without any change, we have to put e raised to plus j omega the same value, 2n1 plus 1 whole divided by 2 here, minus e raised to minus j omega into 2n1 plus 1 by 2 here, right? Then only this factor turns out to be unchanged here. Okay, so that is about the numerator. Divide by, what is the denominator? Again, do the same procedure. Here it is e raised to minus j omega. You take e raised to minus j omega by 2 common out of the bracket. So e raised to minus j omega by 2 out of the bracket. Same procedure we have done in the numerator. Okay, and now what happens to this value? This becomes e raised to plus j omega by 2 to maintain it as 1, right? When you multiply this thing and this thing, you will get 1 here. No change. Okay, simple. Minus e raised to minus j omega by 2. Only if you put e raised to minus j omega by 2, this function will remains unchanged, right? If you multiply e raised to minus j omega by 2 into e raised to minus j omega by 2, it becomes e raised to minus j omega. That's here, right? Now this is very simple. This is I can write this e raised to j omega n1 into e raised to, I can spread this bracket out. So e raised to minus j omega into, or I can write it as 2n1 plus 1 divided by 2 will be n1 plus half. Okay, I'm dividing it throughout by 2. So, and I am taking this e raised to j minus j omega by 2 to the numerator. So it becomes e raised to plus j omega by 2 into, what is inside this bracket? This is of the form e raised to j theta minus e raised to minus j theta. That is 2j sine theta. So instead of theta, it is sine omega into, I can write 2n1 plus 1 by 2 as n1 plus half, like we have did here, right? Okay, so that is in the numerator. And what is in the denominator? It is yeah, this thing has been taken to the upside. So this is remaining. What is this? This is e raised to j theta minus e raised to minus j theta. Again, it is in 2j sine theta form. So divide by 2j sine omega by 2. Okay, you can cancel 2j here. Okay, so that is equal to, we can have some simplifications here. Here you can see e raised to j omega n1, e raised to minus j omega n1 plus half. I'm going to expand this bracket and append this whole exponent to the single base. So e raised to j omega n1 minus j omega n1 minus j omega into 1 by 2. Okay, into, again there is an e raised to j omega by 2 here, this thing. Okay, into sine omega into n1 plus half. We cannot do anything further. Divide by sine omega by 2. Okay, so this is you can cancel these terms. So here it is e raised to minus j omega by 2 into e raised to plus j omega by 2 into sine omega into n1 plus half by sine omega by 2. You can cancel these. So the final answer is, the DTFT of that signal given is equal to ratio of sine omega into n1 plus half divided by sine omega by 2. This is the final answer. And the next question is, state and prove the convolution property of DTFT. That's a very straightforward question. The statement is, if x of n is a discrete time signal, discrete time aperiodic signal whose Fourier transform is x of omega, if y of n is another discrete time signal with Fourier transform Yeah, this is discrete Fourier transform. So let me not confuse you. I can use x of e raised to j omega. Okay, this is a standard notation for DTFT. Y of e raised to j omega. Although putting small letter omega is not wrong, but the standard notion is, notion is actually capital omega. Okay. So x of n and y of n are two discrete time signals, aperiodic signals with DTFT, x of e raised to j omega and y of e raised to j omega respectively. So what convolution property says is the Fourier transform of x of n convolution y of n will give you the product multiplication in frequency domain x of e raised to j omega into y of e raised to j omega. So the hectic operation in time domain, that is convolution, is transformed into symbol multiplication in frequency domain. So that's the biggest advantage of convolution property. Now let us prove it. Okay, so DTFT, what we have to find out is the DTFT of x of n convolution y of n. You know the DTFT of a signal. DTFT of a signal x of n is given by sigma n equal to minus infinity plus infinity x of n into e raised to minus j omega n. Okay. Similarly, what is the DTFT of x of n convolution y of n? Instead of x of n, you are dealing with x of n convolution y of n. Okay. So the result is sigma n equal to minus infinity plus infinity. Instead of x of n, I have write x of n convolution y of n. So x of n convolution y of n into rest is e raised to minus j omega n as per definition. Okay, so this is equal to sigma over n equal to minus infinity plus infinity, and I know how to expand x of n convolution y of n. We have studied in the first module. So this is sigma over k equal to minus infinity to plus infinity x of k into y of n minus k, right? This much is nothing but the definition of convolution sum, x of n convolution y of n. Okay, so the rest is e raised to minus j omega n. All right, now let me do some rearrangements. I can write sigma over k equal to minus infinity plus infinity first, then put x of k then, and since this sigma is on the dummy variable n, and this signal and e raised to minus j omega depends on n, I can group them together. So sigma over n equal to minus infinity to plus infinity y of n minus k into e raised to minus j omega n. Okay, now let me invite your concentration on this summation. What is this? You have to make note that here the signal or variable is n. So this if this is a signal, then the variable of the signal is, or independent variable is n. So k is a constant. Okay, here also n is the variable, there is no k, so this k is a constant. So y of n minus k means you are shifting the signal y of n by k units. Okay, so what is sigma y of n minus k into e raised to minus j omega n? It is nothing but the Fourier transform of y of n minus k, right? The Fourier transform, I can indicate it as, this is nothing but Fourier transform of y of n minus k. Okay, and what is that? You know the property of Fourier transform. If y of n has a Fourier transform y of e raised to j omega, then y of n minus k time shifted signal will be having a Fourier transform e raised to minus j omega k, right? E raised to minus j omega k times y of e raised to j omega. Okay, so let me replace this this whole thing by this expression. So that implies sigma over k equal to minus infinity to plus infinity. There is no change in first summation and x of k, but the remaining thing I can write it as e raised to minus j omega k into y of e raised to j omega. Okay, now listen carefully. What is this summation? This is nothing but a standard derivation, standard definition for the Fourier transform of x of k or x of n. K is a dummy variable. I can always change it to n. Sigma n equal to minus infinity to infinity x of n into e raised to minus j omega n, which is nothing but the Fourier transform of x of n, and I can represent it as x of e raised to j omega, nothing but the Fourier transform of x of n signal. So this is equal to x of e raised to j omega, and remaining is multiplied by y of e raised to j omega. So that is the proof. The next question is explain the relation between Dtft and Z transform, and explain whether Dtft can be obtained from Z transform for first question x of n equal to a to the power e of n, and second x of n equal to u of n. So the first part of the question is explain the relation between Dtft and Z transform, and I think we have elaborated this question. I mean, it very much explained all the derivations and concepts of this question in one of the previous videos. So I think you will refer to that. I'm not going to spend so much time on that, but still I will explain whatever is needed. So in one sentence, the relation between Dtft and Z transform is Dtft is same as Z transform, not everywhere, but only when evaluated along the unit circle. When evaluated along the unit circle in the z plane. Okay. So this is the one word answer for the question. Explain the relation between Dtft and Z transform. Dtft is same as Z transform when evaluated along the unit circle at the z plane. Okay. So why this and all, you may have to refer to the previous video. You will get the good concept on that. Okay. Now explain. Next question is explain whether Dtft can be obtained from the Z transform. Okay, Dtft can be obtained from Z transform for two questions. Okay. So for that, let me tell you, I've seen many textbooks where it says that you can find the Dtft from Z transform just by putting z equal to e raised to j omega. That means suppose you have a Z transform given by x of z is equal to z by z minus a, then the Dtft can be simply evaluated by x of e raised to j omega is equal to, put z equal to e raised to j omega by e raised to j omega minus a. I've seen many textbooks mentioning like this, but according to me, this is only partially right. This is only partially correct, because for all Z transform, you cannot put z equal to e raised to j omega. You cannot put for all Z transform, you put z equal to e raised to j omega and obtain the Dtft. That is wrong. Why? Because Dtft exists. You have to listen very carefully. Dtft exists only if for the corresponding particular Z transform, the ROC, only if the ROC includes the unit circle. Includes the unit circle in Z plane. You can relate that to this statement because Dtft exists only when Z transform is evaluated along this unit circle. Okay, so whenever you get a Z transform, you have to first check, the primary checking should be whether the ROC of this Z transform includes the unit circle. If it includes, only if it includes, you have to listen, only if it includes, you can put z equal to e raised to j omega and will arrive at the Dtft. Okay, so that's the important result here. You cannot simply blindly put z equal to e raised to j omega, but you have to test whether the ROC of the Z transform includes the unit circle. If it includes, you can simply put z equal to e raised to j omega and obtain the Dtft. if the ROC does not include the unit circle, you can put z equal to e raised to omega, but whatever you get as DTFT will never exist. So that is wrong. Okay. So we have given two questions here, x of n equal to a to the power of n u of n. So we'll start working on that. The first question is x of n is equal to a to the power n u of n. Okay. So what is the z transform? Z transform is equal to z by z minus a. Okay. What is the ROC? I've told you the first step is to evaluate the ROC. If it includes the unit circle, then you can put z equal to raised to omega and obtain DTFT. So what is the ROC? Here, ROC can be specified only if you get the value of a, whether mod a is greater than 1 or mod a is less than 1. Okay. If ROC is mod z greater than mod a. Right, mod z greater than mod a. Why? Because this a raised to n u of n is a right-sided signal, so the ROC will be outer to the pole. Pole is z equal to a, so mod z greater than mod a is the ROC. Fine. Now the primary concern for us is to decide whether this ROC includes unit circle. Does it include unit circle? It should be decided only if you know a. If mod a is less than 1, for example mod a equal to half, then it includes the unit circle, right? Because this is a z-plane, and suppose this is the unit circle, so this is 1, half will be here, so mod z greater than half means you consider a circle at half, so this entire portion mod z greater than half will be the ROC, which clearly includes the unit circle. So when mod a is less than 1, then ROC includes unit circle. Then only ROC includes unit circle, otherwise it does not. So we can arrive the DTFT by putting z equal to e raised to j omega, provided mod a is less than 1. Therefore DTFT x of e raised to j omega will be equal to for z by z minus a, put e raised to j omega for z, so e raised to j omega by e raised to j omega minus a for mod a less than 1. Okay, so this is the answer to the first question. The second question is x of n equal to u of n. Okay, here x of z is equal to, you know the equation, z by z minus 1. Okay, and the ROC is mod z greater than 1. So here ROC is mod z greater than 1 means it just includes the unit circle. This is unit circle, so mod z greater than 1 just includes the unit circle. So it just is a marginal existence, right? So since it just includes the unit circle, DTFT exists marginally, and it can be evaluated by putting z equal to e raised to j omega. So x of e raised to j omega equal to e raised to j omega by e raised to j omega minus 1. So the conclusion is, for both of these questions, DTFT exists and can be obtained from Z transform. But for the first question specifically, this stands only for mod a is less than 1. Okay, mod a is less than 1. So that concludes the answer.